Now, rather than providing a formal definition, I'm going to have you guys invent the trie. I'm going to do that by inserting 2 keys, myself, and then let you do the rest. So ultimately, your goal is to build a set containing sad, alls, same, a, sam, and sap. And here, what I'm showing you is what a trie looks like that has already got sam and sad in it. So let's look at this and think carefully about what's going on. In our trie, it's a tree of nodes, where each node stores 1 letter. And importantly, each node can be shared by multiple keys. So here, sam is the node S, followed by the node A, followed by the node M. And sad is the same 2 first nodes, and then a D at the end. So to see if that makes sense, what I'd like you to do is add sap, same, a, and alls, and then I'll give you my answer. So you're basically just inventing the trie right now. Okay. So hopefully you had a chance to try it out, and I will give you my answer by doing it here. Actually, let's do it on this slide. So we got to insert sap next. Well, we already have SA, so we just need to add in here a P. Okay. So I'll add this P and I'll add a line. Oops. All right. So next up, we got same. So we've already got sam, and so again, we just need to throw in ourselves a little E, and we end up with same. Okay, well, it says samp right now, but we'll fix that in just a second. There we go, we got same. How about A? What's A gonna be? Well, we can't use this A. Like, it wouldn't make sense to do this. Like, you could try and do something like that, but I don't like that approach because it's just very strange, because then I don't really know if this is the letter A by itself or if this is the beginning of aim or what. So instead, what I'm going to do is create a totally new A and put it over here. So it turns out that's the right approach. But if you came up with the other thing, that's fine. And then here, I will now need to add in, well, once I do alls, I'm going to reuse this A. So I'll just grab these here. And it's not pretty, but I'll have a prettier version on the next slide. So here I have A, W, L, and S. Okay, so that's my trie. Though I have one tricky issue that remains. We're not totally done, because at this point, it is not clear to the user, or looking at this diagram, which keys actually exist. So for example, we're supposed to have sam, sad, sap, same, a, and alls, right? However, it's not clear, there's no way to know that A is in the set, but all is not, or that all is not. So what I'd like you to do now, your second challenge, is figure out a way to make it absolutely crystal clear that this set contains exactly sam, sad, sap, same, a, and alls. And I'll give you a hint, which is you don't need to change the links at all. Okay, so my approach is that we should go to the last character of each key and just set its color, let's say, to blue. Oops, wrong color. And that will indicate that that key, or sorry, that letter is the end of a key. And so here, now, finally, we have a trie. Okay, so that's how tries work. Now to get a better intuitive sense for how contains should work, let's consider these following contains operation. So this is the trie that contains sam, sad, sap, same, a, and alls. We're done with understanding the insertion operation. So contains works like this. We start at the root, and then we consider the first letter, S. Okay, we go down here, S. Then we go to the next letter, A. Then we go to the next letter, M, and we find that we've ended on a blue node. So we will return true. Okay. Well, how about contains SA? So in that case, we start at the root, we follow S, we follow A, and we're still in the tree, but the node we've ended on is false. It's a white node. This is not the end of a key. How about contains A? Well, in that case, we go to the left, we get to A, and this one's blue, so we return true. And then lastly, imagine SAQ. So we'd go S, then A, and then we'd fall off the tree, trying to find the next node, and so we would return false. So these two cases are sometimes known as a hit and a miss. So a hit is whenever we have a true, and miss is whenever there's a false result. And so there's essentially two ways to get a miss. One is if the final node is white, and the other is if we just fall off the tree. For example, we do SAQ or SAX. So now we understand both insertion and search, And so I'll just briefly mention that tries, these data structures we've talked about, they can also be maps. It doesn't have to be a set. So a map is very simple. The only difference is that inside each node, we will store not just the letter, but we will also store the value associated with the key ending in that letter. So for this example here, this trie maps the string by to 4. It maps she to 0, and so forth. And if you want to see a visual demo of this tree getting constructed, it's pretty much just what we saw. There is here a QuickTime file that you can watch. All right. So to summarize what we got here, we had our BSTs before. We invented also a hash set, and now we have a trie set. Okay. Now, one last thing before we proceed is the name. So these are known as tries, which is short for retrieval tree. That's a very strange name because trees are often used for retrieval anyway. So I really don't like the name. Like BSTs, also you could argue are retrieval trees, but whatever. But its inventor, Edward Fredkin, was being clever and said it's a retrieval tree, so it should be called Trie. But of course, that's the same word as tree, so everybody basically said, no, we're going to just say trie. And if you look on Wikipedia, there is a debate here where someone complains and says this was a really bad choice because you can't distinguish tree and trie in that case. So be aware that if you wanted to honor the inventor, you'd call it a tree, but we just don't. We call it a trie. All right, so that's the idea of a trie. And so from here, we'll start picking apart the more fine implementation details as well as its performance.